In this video, I'm going to show you 3 different ways to argue that 2 different logical forms are actually logically equivalent. So what do I mean by this? I'm going to begin with a particular pair of logical forms, not P or Q and not P and not Q. And the question is, are these 2 different things the same or are they going to be different? In fact, they're going to be the same, and it's going to be a very important law in logic called De Morgan's law. But how can I figure that out? Now, the first one I'm going to do is not really much a proof, but it's sort of test of reasonableness. I want to just make up some example, make up a P and make up a Q and see whether you can just sort of reason it through and get a result that makes it look equivalent. So, for example, what if I set to be P is Trevor is a unicorn and Q is Trevor is a goldfish? Something ridiculous. Now, if I think about the left-hand side here, so the not P or Q. So P or Q stands for Trevor is a unicorn or Trevor is a goldfish. And then when you put a not all the way out the front, what you're saying is that it is not the case that Trevor is either a unicorn or a goldfish. That's one way I could come up with an English sentence for that logical expression. Now, for the right-hand one, I'm saying not P and not Q. In other words, I'm saying that I am not a unicorn and I am not a goldfish. Now, it's a silly example, but if you look at these 2 different things, do you think that they are the same, they express the same idea, or a different one? Well, if I look at the left-hand side, if I'm saying it is not the case that I am either a unicorn or a goldfish, it really means I can't be either of those. Which is basically what the right hand is saying as well. It's saying I can't be a unicorn and I can't be a goldfish. So it seems reasonable to me, but maybe you say, well, hold on, that's not actually a proof, I want something more. Now, the way we had defined a logical equivalence was to say, go and look at the truth table. So here is this truth table for the so-called De Morgan's law. I set my P and Q to be a bunch of different true and falses. I have some intermediate values that I've put here, like the not P and the not Q and the P or Q. And then finally, the final 2 columns are the left-hand side and the right-hand side. And you'll notice that because they match, because it's false, 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 true, that means these 2 different sides are logically equivalent by definition. So this is the more formal proof of the reasonable test that our sort of English sentences gave us. Now, there are an enormous number of these logical equivalences out there. There's a couple that are pretty major, so we can list them off by name. This one that I did is De Morgan's law, but there's actually 2 versions of De Morgan's law where you permute the or and the and statement. But we've seen previously we had a double negative law. We had a truth table that showed the negation of P was P. And then when we talked about tautologies and contradictions, there were also a bunch of different laws that applied there. There was these identity laws that said if you took something like P or a contradiction, that's just P. There were these universal bound laws like that P or a tautology was a tautology. And there's many more that I haven't put up on this list. So this brings me to my 3rd way of showing a logical equivalence. You don't always have to go back to a truth table. If you want to, now that you know all of these are logical equivalences, you can cite them in the proof of a new logical equivalence. Let me show you what I mean by this. Let me begin with this messy statement over here. What I'm going to try to do is clean it up, manipulate it into some other logical statement, but where all of my manipulations are the rules that we just saw on the previous slide. That is, I'm not doing a truth table, I'm applying a list of rules. So, when I look at this thing, there's many ways I could start, but the first is I could apply a De Morgan's in the middle. There's a not, and then there's an or statement of 2 different things. So, let me do that. Let me apply my De Morgan's law. So what happens? The not goes in front of the P, the or flips to an and statement, and then finally, the left-hand side and the right-hand side, there was this not Q. So when you bring the new not in, what you get is not Q. And then finally the and the tautology on the out-hand side. I haven't touched that one at all. Okay, well, now I could do a double negative thing. I have a not Q here, so let me apply my double negative rule. And so this is just not P and Q. And then finally, and a tautology. Okay, it's already got a little bit cleaner. Well, what about this thing where I've got a big thing in brackets and then I put and a tautology? Can I clean that up? Well, one of the rules we had before, an identity rule, is if you have any statement, you go and a tautology, that is exactly true and exactly false based on the original statement. The and a tautology part doesn't do anything. So by this identity law, we can just get rid of the and a tautology thing. And so now we've cleaned it up when we say this is logically equivalent to not P and Q. So the point here is that you don't always have to go back to a truth table, which can be somewhat long and cumbersome. If you have this list of known logical equivalences, you can apply them in sequence, citing the name of the logical equivalence as you do, and you're able to take one logical form and manipulate it into a different logical form.
So far, we've been investigating statements, as if they're just this thing that I might just utter for fun. We've got the statement and we've been investigating, is it true, is it false? We try to take a statement and break it up into its logical form. But what we really want to be doing is making arguments that persuade us that conclusions are going to be true. So a valid argument is going to be this list of statements that we're going to refer to as premises. And then if you accept all of these different premises, then the conclusion logically follows. That's our real goal. We want to be able to prove theorems, or we want to argue to somebody why something might be true. We're going to try to come up with a logically valid argument that does this. Now, the idea of a logically valid argument is to say that the structure of it is indisputable, that we can not dispute that the conclusion follows from the premises. There might be other ways to go about it. You might have many criticisms of the argument. For one, you might say, well, look, the premise that you told me, it isn't even true. So then the conclusion doesn't follow if the premises aren't even true. But if you've written a valid argument, then everybody should be able to agree that your argument is indeed valid in the sense that the conclusion does indeed follow from the premises. So here's a sample argument. I've broken it up into a couple different parts. I say, first of all, if I do the dishes, then my wife will be happy with me. This is just a premise. Not saying it's a true premise, not saying it's a false premise, but it is a statement, and in particular it's a conditional. Then I'm going to make the claim, I do the dishes. And then the conclusion here is that my wife is happy with me. Now, both of these premises may not be true. Maybe I don't do the dishes. Maybe this is way too simplistic of a statement to deduce my wife being happy with me. But the logic of it, I think, is sound. If I have this one thing, if I have this hypothesis, then I get the conclusion. I'm assuming that I do have the hypothesis, therefore I do get the conclusion, and I have this structure. So let's just look at the structure for itself for a moment. Now I filled it in with a kind of joke example here. But I could fill in this structure with anything. For example, I could just put P's and Q's in place of these statements. So where I had I do the dishes, in both of these two places, I'm going to put it to a P. And when I have my wife will be happy with me, I'm going to replace those with Q's. So this is what we refer to as a logical form, or an argument form. And in particular, it's one that's got a name of modus ponens. Now, modus ponens is, it's a fancy Latin name for it, but what it means is a logical structure of the form, if P then Q, so if an assumption then a conclusion, and then you take that assumption, and therefore you get the conclusion. Now, I think that this argument seems relatively reasonable. If you have an assumption, then you get the conclusion, and I assert you do have the assumption, so therefore you do get the conclusion. That seems intuitively reasonable to me. And indeed, I think we use arguments like this all the time in our daily lives, although we may not structure it quite so explicitly. However, let's try to look at the level of truth tables to verify that this argument that intuitively makes a lot of sense actually is indeed valid. So the first thing I'm going to do is I'm going to put down my variables. I'm not going to fill them on myself because we do the same thing every single time. So I got my variables P and Q. So if I go and look at my argument, I've got these three different lines. The first of them I will sometimes call P1 for premise 1. And then the second of the two I will sometimes call P2 for premise 2. And then the third of them I might call C for conclusion. So what I want to do in my truth table is to now put up my two premises. So here we go. We have the P implies Q and the P. So first of all, the P implies Q. We know true, true. This is going to give us a true as well. Then we're going to have true, false, that's going to be false. And then I have these two false down here in the P column, and so we got the vacuously true scenarios, so I can put true, true in there as well. And then I'm sort of just repeating myself. I've also put P because P was a premise, but P was also a variable, so I'm gonna kind of just copy and paste this particular column, so it's a little bit tedious, but whatever, that's all right. And I'm doing it in this way just because I want to have one sort of block here that's got all of my premises. So even though P, which was a premise, just happened to, by coincidence, be a variable as well, I'm gonna put it down in this section over here. So there, I got my variables, I got my premises. Final thing I wanna write down is my conclusion. All right, so my conclusion is going to be Q, and what we're trying to say is that in any scenario where both premises are true, we want the conclusion to be true as well. But if I look at my premises, there's a false here, there's a false here, there's a false there. The only one where both premises are true is this one. And so I care about this row, and in this scenario, true, true, and if I look over at what Q was over here, Q was true as well, so what do I get? I have a true. And then I actually don't even care to fill in this part at all. It doesn't really matter to me what goes in there, because in this scenario, the premises are not satisfied. In this logical argument, I am assuming that both of my premises are true, and if my premises were not true, I don't care. My argument doesn't matter whether it's valid or not. So all that matters in this scenario is this first row here, just because that's when all of the premises are going to be true. And what do we have? Indeed, the conclusion is true because it matches the claim over here. The variable Q is the same thing as this. So I think yes. I think this is logically valid, that modus ponens does indeed work, and the intuition is proven by our truth table. Another very famous and important logical argument is a form referred to as modus tollens. And this is the statement. It's one premise, if P then Q, a second premise, not Q, and the conclusion, therefore, not P. And the idea here is that if you have a conditional that P implies Q, but that your conclusion is false, it could not be that your assumption was true. Because if your assumption was true, your conclusion would have to be true as well. So knowing your conclusion is false forces the assumption to be false as well if you have this conditional. If we wanted to, we could go and write out the truth table exactly as we did for modus ponens, and we could get that indeed the columns matched, and so we would have that this argument form was going to be valid. I'm going to note that both modus ponens and modus tollens are referred to as syllogisms. These are examples where you have two different premises, sort of a major premise and a minor premise, and therefore you get a conclusion out of it. So let's see an example of one of these. Here's my argument for it. If I'm the President of the United States, then I'm an American citizen. I am not an American citizen, true fact, I happen to be a Canadian, and therefore I am not the President of the United States. Now, this is not the only way I can prove that I'm not the President of the United States, but it is one argument that is logically valid, and in fact, both of these different conditions are going to be true. You have to be an American citizen to be the President of the United States. I am not an American citizen, therefore it must be that I am not the President of the United States. And indeed, if we come through and try to look at our structure here, I'm going to say that I am the President of the United States. That's going to be my P here. I am an American citizen. That's going to be the statement Q. And then what I'm doing down here is that I am negating this. I am saying I am not an American citizen, and therefore I am getting out of this not being the President of the United States. So I have proven that I am not the President of the United States.